Welcome to Subatomic Tanvi.
Hi, everyone.
In the last episode, you mentioned we're going to talk about fermions and bosons. Are we?
Of course we are. They're the coolest cats of the subatomic jungle.
Interesting you call them cats. Maybe we invent a machine that'll make them my pets?
That'll be a mystery for another day. But for today, we're going to talk about the families of particles that are responsible for the universe and the two groups of particles that are responsible for making everything happen.
I hope the two groups are called fermions and bosons.
You bet. We got fermions, the lone wolves of the particle world, and we got bosons, the social butterflies who love hanging out with each other.
Lone wolves, so there are no subatomic pool parties for them? That's sad.
Well, you might say that now, but wait until you hear about bosons. Let's start with fermions, though. So fermions have a half integer spin, like half, one and a half, two and a half, three and a half, and so on. Fermions spread out, unlike bosons, which clump together. And since fermions spread out, this is why they're capable of creating all the matter around us.
That's why you call them lone wolves, I guess, because they spread out away from each other instead of clumping together.
Exactly. And fermions also obey the Pauli's exclusion principle, which states that no two fermions can share the same no two identical fermions can share the same quantum state simultaneously.
Can you talk a bit more about Pauli's exclusion principle, like how kids like me can understand?
Well, okay. So imagine the Pauli's exclusion principle as a concert. So let's say that the venue at the concert only has a limited amount of seats, and there's no seat sharing allowed, so no two friends can share a seat. This is just like the Pauli's exclusion principle. It's the first rule of it, but obviously instead of with people, it's with particles. The second rule of the Pauli's exclusion principle is that if two friends absolutely must share a seat, you can, but with a twist. Both the friends need to be facing opposite directions, just like two entangled electrons having opposite spin measures. If you recall what I said in the first ever episode of this podcast, I mentioned that no two entangled electrons can have the same spin measure. They always have to be opposite. And well, this is why the Pauli's exclusion principle.
I remember that. I think it's all coming together now. So, how does this help in the formation of matter?
So, if all the fermions, instead of spreading out, if they clump together the way bosons do, atoms would be so tiny and unstable. But the Pauli's exclusion principle forces fermions to spread out, which gives atoms their size and stability.
Got it. Now, let's talk about bosons. You said they do pool parties?
Not exactly pool parties, but they're the opposite of fermions. Fermions are responsible for creating all the matter around us. And on the other hand, bosons are responsible for carrying the interacting forces in between the particles as their force carriers.
Got it. But why do bosons clump together?
If you chill bosons down to absolute zero or 0 Kelvin, they start coming together and they just clump together into one giant particle, and they also have some interesting properties like superfluidity. So an explanation for superfluidity is, imagine if you're just holding a cup of coffee, not even moving, doing nothing, just holding it, and then the coffee just climbs over the edge of the cup and starts spilling out when it's not even moving.
Ooh, that's straight from a science fiction movie.
Well,
What are we going to discuss next about fermions and bosons?
I'm just going to bring up a model of the standard model of physics and explain that. So this is the standard model of physics. This side is fermions, this side is bosons. So here we have the quarks, the leptons, electrons, muons, tau neutrinos. All of these are leptons, and these are the 6 types of quarks that we spoke about in an earlier episode. If you can recall those, the up, down, charm, strange, top, and bottom quarks. And this side are bosons, which are the force carriers, gluons, the force that kind of sticks the quarks together, which I also explained in the quarks episode. They are bosons, and these are some other types of bosons: photons, the particles of light. And in a future episode, we're also going to be talking about something very interesting called the Higgs boson, which is over here.
That's wonderful. Thank you so much for explaining everything about fermions and bosons and for introducing all of us to the standard model of elementary particles.
You're welcome. Bye, everyone.